So the key estimating steps will be the ones that is most, I think, the most mathematical section of this part. So bear with me. Overall, I think it's doable and definitely like straightforward to some degree. And I think based on what we have known so far about, I mean, from 347 as well as all of the review and as well as the new material that we talked about at the beginning of this course, doing Bayesian synthesis and all that, I think overall this will be straightforward. But of course, I will take certain effort to get a solid understanding. Okay. So equation 3 is strictly using Bayes' rule. Okay. So what we're doing here, as you can see, is that if you think about this as a quantity that you're trying to get the conditional probability of, and you can think of this as a parameter in some sense, but I mean, in the Bayesian method, I mean, the modeling that we've been doing, think of it as a parameter, but right now, just think of it as a quantity. So what that, using Bayes' rule, what that can help us is that now we, so the goal is this quantity given the synthetic data and then any assumption that we made about the intruder's knowledge, right? And this can be turned into, by Bayes' rule, using proportionality, that we can find, it can be proportional to the product of Z. Remember, Z is what we have for the synthetic data, right? So it could be proportional to this distribution, Z given what we are guessing, and then all of the assumptions, right? Multiplies with, we can think of the second term as the prior, that before knowing anything, what is the prior of the, say, prior probability of a particular guess that I'm making right now? Okay. So this is strictly Bayes' rule. And notation-wise, we're using Y star to represent one possible guess of YIS. Okay, so if we come back to the example that I was saying, that if it's a univariate categorical variable, you have 6 different guesses for a categorical variable with 6 levels. So Y star would just be one of them. Okay, but essentially we're going to evaluate for all of the 6 because we want to know whether the true one will have a really high chance to be guessed correctly. Okay. And again, YUS, A and S, they're whatever information available to the intruder, we have to keep making assumptions about them soon when we try to, I mean, for example, if you look at the second term, well, how do we know what that is, right? If you think about, we have to assume certain things about A and S when we're doing this, and similarly here as well. So keep in mind, we altogether write all of this as what is known to the intruder, but we do break them into separate pieces just because it's easier to differentiate in this way later when we're doing the computation, okay? So the part that I just circled up here, if we look at the third bullet point, it is the synthetic data distribution given what the intruder knows, right? If you look at it, what it is, it's Z is the synthetic data set. It's given a particular guess of this YIS, is Y star, and then what is unsynthesized, and then the auxiliary information and any other information known by the intruder about the synthetic process. Okay? So this is, I would say, the most challenging thing to estimate, as you will see soon. But I mean, just looking at what it represents is the synthetic data distribution given what the intruder knows. And it is here, I think we have to make very strong assumption just to make the computation workable, and you will see soon what we need. The last one is about the prior. You can think about the prior information on guessing this particular Y star given everything else the intruder knows. So that's what we mean by Bayes' rule being applied to this particular situation. But overall, I think, like we were saying earlier, you have to make a lot of assumptions, but at least at this step, I think, I mean, it's still mathematically sensible. I mean, in a way that it's natural thing to do. All right, okay. So we're gonna look at the 3 different pieces of information one by one to see what they know, okay? So the knowledge of YUS, we talked about it early on, especially for partial synthesis, because the intruder will have access to the released synthetic data. So any unsynthesized information the intruder will know, right? So most of the time for partial synthesis, the knowledge of YUS will just be completely available to the intruder. Right? For the full synthesis, we know that the unsynthesized variable set is empty, so the intruder wouldn't know anything. But for the partial case, which is the one that we're going to focus on, it's readily available to the intruder. Okay? So that means, I mean, in context, the CE data, we know that we only synthesize income, right? So only income is synthesized. So there are 3 other variables never synthesized, right? So then, because, well, in the synthetic data, Z, the first 3 columns is never changed, and only the income is changed, right? Because it's synthesized from the model. So what we mean by YUS is the 3 column here, okay? And that 3 column, because Z is available, and if the intruder also knows that they're only synthesizing, like what's being released is only having the income synthesized, so that means that they will have everything in the YUS. Okay? So think about what that means in your project, and you might have some idea what you are trying to do. And so without loss of generality, we're going to use YUS, even though we recognize that for full synthesis, YUS is an empty set. All right, assumptions about A. So this is the one that we're going to make super strong assumptions. So bear with me. Let me just talk about what we do, and I will illustrate why we do that. So A, we know that is auxiliary information known by the intruder about records in Y, right? And we know that Y is the union of YUS and YS, right? So YUS is the synthesized set, unsynthesized set, and YS is the synthesized set. So we know that YUS is already known from the previous slide, okay? So now the assumption is, what else the intruder will know that is in the YS, okay? So as you probably have been guessing, numerous possible scenarios. And the one that we're proposing here, I'll show you, is what we mean by super strong, okay? Is we assume, so it's the worst case scenario, what we mean by that is that the intruder, so let's say the intruder now focus on record I, okay? The intruder is trying to infer the true value of the record's I's synthesized value. So we assume that when the intruder is working with record I, the intruder knows everything else except for record I. Okay? So the notation here is that A, which is the set of auxiliary information known by the intruder, is YS -1, negative I. So this subscript, -1 or minus I, sorry, negative I, minus I, meaning that it is every record except for I. Okay? So what this means is that, remember, we have that little graph that I was doing earlier. Income is synthesized, right? 3 variables, they are in the YUS, so that's all known by the intruder. So let's just say we're trying to evaluate risk for this I record, okay? What we mean here, once we make the assumption about A in this case, is that the intruder knows all of the shaded information except for that record. Okay? So this is saying, it's a little bit unrealistic, I agree. But what this is saying is that when we're trying to evaluate the risk for this record I, the intruder, first of all, knows all of the YUS because those are unsynthesized, it's publicly available in Z. Okay? But the intruder also knows all of the actual value of the synthesized income for all of the other records except for I. Okay? So it is very strong intruder knowledge because we assume that intruder probably knows everything except for the one that we do like evaluate right now. It is strong but also conservative because what I was saying earlier, similar to what I was saying earlier, if the attribute disclosure risks under such conservative and strong assumptions are acceptable, then under any weaker assumptions, the attribute disclosure risk should be acceptable as well. Okay? And also, full disclosure, it is making this assumption, strong assumption, can be more, yeah, I mean, the computing will be much easily done later. Okay, so bear with me, but I agree at this point, making this assumption is very strong. And we call it worst case because we can think of that the intruder wouldn't know much more beyond this, right? This is all the intruder could have known. If the intruder is trying to find, or not find, sorry, trying to guess the value of this yi, we assume that the intruder knows everything else. Okay. Right. The last piece is about this S. Okay. So I was saying earlier as well, like synthetic LBD, for example. That's the synthetic longitudinal business database that is publicly available on Census Bureau website, but we also read about that paper, how they do the synthesis, right? So information about how about the process of generating synthetic data, Z, at some point, I mean, sometimes I should say, is also publicly available. So we will assume those are known by the intruder as well. Okay. So that's what we mean by S. And those will be examples. It could be code, it could be descriptions of the synthesis model. But imagine, I mean, as an intruder, they probably want to utilize all of the possible information that they can get when they're doing this kind of attacks, right? So this will be what we assume that they know. All right, so that's about the SLD, okay? The last one is choosing the prior, okay? So the prior is coming from here. You remember, this is the prior. And we call it prior because, well, this is a particular guess, right? We're looking at, so this final distribution or probability that we're trying to estimate is the probability of guessing, I mean, the guess of Y star given the synthetic data and everything else known by the intruder, right? So if that is the case, and that can be thought of as a posterior because you can express your Z given the guess and then everything else. So that left you with this prior. And this prior, if you think about it, is without knowing anything about the synthetic data itself, how likely it is, or what's the probability, or what's my prior belief about guessing Y star given what's known to the intruder. Okay. So a common practice is uniform prior, meaning that, well, if I have 6 possible guesses that I was using the example with, if I have 6 possible guesses for my say marital status for that particular YIS, then I think each one is equally likely. So I'm going to use a uniform prior, which is going to be 1/6 for all of them. So it's a common practice, but some people like discuss pros and cons of each. So that's why I was writing the last bullet point here with a few questions. Do you think a uniform prior is reasonable? In what situation using it makes sense? When might you overestimate or underestimate the attribute disclosure risk using a uniform prior? Okay, so you can use the example that I was using, thinking about univariate categorical marital status outcome. Okay, 6 different categories using 1/6, a uniform, or anything else. And what are you thinking? What situation you might overestimate or underestimate? And I will leave the page here, but I understand once you go to the breakout room, you might not be able to see it. But again, this is on page 15 of the lecture slides. So if you have it open, take a look at that. So it's about the question now, like the set of questions is, in what situation you think uniform prior is reasonable, in what situation you think it's not, and then maybe come up with some scenarios that you think, well, using the uniform distribution might overestimate or underestimate for a particular. When we say underestimate, it's really just underestimate the final thing here. Okay, we haven't talked about how to, let's just say, we haven't talked about this part yet. Okay, so you can think about, well, regardless of the prior, that is fixed. Okay, but so now we're thinking about in what situation a uniform prior is useful, or in what situation it's probably not that useful, and all that. Okay, so let me pause here. So anybody wants to share, maybe just report back from what your breakout room was discussing, or any conclusion, share comments? Isaac, yeah.
Yeah, so one possibility we had, like, this is kind of the first one is kind of a cop out, um, like you might not want to use a uniform prior if like there's something more conjugate available. Um, so that's like the cop out answer. The other one, we were wondering, like, we think you'd overestimate if, say, you had a like maybe an exponential distribution, and I could
Mhm.
totally be wrong, that doesn't have a mode necessarily. So it's like is the camera in reverse when I?
We couldn't tell if it's reversed. Uh,
Okay, I'll go like, so it's like this exponential distribution, but
okay.
then the
No, that's
uniform
right. Yeah.
proposing things like way out here when the bulk of the density's in
Oh,
there.
I see. I
I
see.
don't know if that picture's wrong. Flip it.
Right.
Um,
Yeah. So good
and we
point.
think maybe you'd overestimate there, but not necessarily.
Yeah. So I guess right. So I think both. Yeah, the two answers. I mean, about whether we can use a more conjugate case or whether it's overestimating. I think it's. I guess conjugacy is about the relationship between these two, right? And then the overestimating is, well, whether like if there's a true prior distribution that we should use, then uniform, well, depends on in which case it's either, I guess, overestimate or underestimate, right? Mm-hmm. Yeah, so good point. So it's interesting that, I mean, your group talking about conjugacy. So I think, right, so, well, this is the prior, and then we know that you can think about the other one, the one above it is the likelihood for sampling model. So that will be a way where we might want to use conjugacy, right? I mean, if it's easier for the estimation. The thing is, once we get to the next step, as we go into how to estimate this part, you realize that that part most likely is not a known distribution anyway. So well, in terms of that, I think whether you want to use a conjugate or not probably wouldn't be that relevant. But if we do find a known or possible known distribution for the first part for Z, given a particular guess and then the intruder knowledge, then thinking about conjugate probably will definitely simplify the estimation of the left-hand side. Okay, so that's good to know. And so I guess maybe let me just put it back into the context we were saying earlier. Let's just say it's about marital status. Okay, it's not in the CE, but since it's a categorical variable with 6 levels, it's probably easy to think about at this moment. So if now I'm trying to guess which level of this person in terms of the marital status variable for this person, and I know I have 6 possibilities to choose from because that's all of the possible values for this variable. If I'm going to use a uniform distribution, would that make sense to you, or would you choose any other prior for this case? Yeah, Sarah?
I was just thinking it might depend on how much data, like how large the synthetic data set is.
Mm-hmm.
So like say the underlying distribution isn't uniform, which I think it is in the case for marriage here. And you have a small, like the data set you're looking at has small,
Mm-hmm.
then your prior would inform probably your posterior more than if it were a larger data set. So when you have the uniform distribution, it would like kind of allow you to underestimate risk maybe. Whereas if you have a very large data set, then it's probably the data that's driving the distribution in your posterior. So in that case, it probably isn't that big of a deal.
Mm-hmm. Mm-hmm. Yeah, interesting. So yeah, so here the prior, which is even though we're using the prior and also the entire base rule setup here, it's I would say slightly different from the way that we usually think about prior and the posterior and all that. But I mean, it's a very common. I mean, especially if I know it's possible to have 6 different categories, should I just use a uniform because maybe I don't have any other better guess of which one is more likely without seeing anything, using a uniform prior? Or if I have in my data set, I know the empirical distribution, for example, of the breakdown of the marital status variable, maybe I should use that instead of using the uniform. Okay, so So those are possible comments or concerns or like ways of thinking. But what I want to say here, I guess, is, I mean, it will become clearer later once we finish like the other aspects of the estimation process. But here we know, let me just break this, yeah. So here we know that this will come into play eventually when we're estimating the left-hand side, right? We use the Bayes rule to break it into this way, right? And uniform prior here is really just for computation, I guess for computation simplicity, because imagine we have 6 different guesses for this Y star, right? So we're gonna do that for each of the 6 guesses, and then we're gonna compare across them in terms of their posterior, right? One of them gonna be the truth. Let's just say the truth is 3, okay? But my Y star will be 1, 2, 3, 4, 5, and 6, right? So I'm gonna evaluate the left-hand side for all of the 5 or 6 different values, right? And then I'm gonna look at my my case for the truth. When truth is 3, I want to see, say, if number 3 will be the most likely to be chosen, to be, or I should say, most likely having the highest probability on the left-hand side. Okay, so in there, you will see that we're going to do some computation, and then we're going to do some comparison. So if you're going to choose a uniform for this part, then they're all going to get canceled out. Say if it's 6, it's 1 over 6. So it's going to be 1 over 6 for all of those, all of the 6 different choices. So the left-hand side, in the end, going to be driven by the estimation of Z given the guess and then the intruder knowledge, right? Whereas, well, if you use a uniform prior, that will be the case. But if you use a non-uniform prior, then you're placing higher weight on certain guesses, right? So it really, I guess, it really depends on what you think will be the case. And related to what Sarah was saying earlier, so it's probably not so much about like how much data you would know, or like how large the data set is, or how big the amount of data that you have. In this context, it's about this term, that if you're using a uniform, that is driving, right, the posterior. If you're using a non-uniform, then you're using this part and the non-uniform prior together to drive the posterior. Okay, so again, I mean, we really don't really call this part as the likelihood or call this part as the posterior, but we can break the left-hand side using Bayes rule to the right-hand side, and then naturally you have these 2 quantities that you have to estimate. And then our big goal and the most challenging part is about the first point, Z given, like all of the other things. We're going to talk about how to do that. But we also have the last part here in terms of they look, I mean, it looks like a form of prior. That is prior because it's the probability of, or your prior guess of guessing this Y star without looking at the data itself. So that's what we mean by prior in this case. Okay. All right, so sounds good. And okay, so the most challenging part, like I said, will be this part. So bear with me. Let's walk it through step by step. So this is the estimation of the density of Z, which is the synthetic data, given a particular guess of YIS, and then all of the other information. Okay, so because you might have more than one synthetic data set that you generate. So this form, the Z, is a collection of all of them. But remember, when we generate synthetic data set, we're using independent parameter draws, right? So that means that when you're looking at the joint of all of the Z, given Y star, and then the intruder knowledge can be the product of each of the ZL, given the guess, and then the intruder knowledge. So that's why instead, I mean, ultimately you make the multiplication of all of those density, but before that, you can work with each particular synthetic data set. So that's what we mean by that. So for notation, we're gonna use a Z superscript L from now on, and then there are M synthetic data sets in the end. All right, so remember, under the worst case scenario, we have what? We have our A includes everything except for the record I, right? So if you look at that, our ZL in equation 5, once we replace A with y minus is, it becomes equation 5. And equation 6 is actually is how we actually generate the synthetic data, if you remember. The synthetic data, ZL, is generated using the model that we fit on y. So remember this y, this little y here. This little y is the original data. Okay? And remember, our model in the first place when we generate synthetic data was fit on the original data. Okay? So if you want to write the original data will be, if we expand it, it will be the same as A, right? A is everything of the synthetic value except for the I's record, all of the unsynthesized records, and then the guess being the true value. Okay? So it's very similar between 5 and 6, okay? So even though I posted as a question, the difference between equations 5 and 6, but once we expand it, you can see that the only difference really is about this part and this part, okay? Equation 5 is what we want to estimate. That is, we're looking at ZL given the guess and then the other knowledge, right, introduced knowledge. Whereas equation 6, which is actually what we could have from the model, because that's exactly how we generate our synthetic data, Z, in the first place. And the difference between the two is the two terms that we circle in blue here. So we highlight this mostly because, well, if you look at equation 5, if that's what we want to do, like we use this worst case scenario, and then equation 5, if I want to estimate this equation 5, what should I do? I should go into my synthesis model, right? I should go back to the synthesis model. I'm going to replace my yi to y star in my original data, and then I estimate the model one at a time. So say I have 6 different guesses, right? I know, so if we go back to the example, the working example, let's say the truth was 3, right? And then we have 1, 2, 3, 4, 5, 6. 6 different possibilities, right? So if I want to estimate my equation 5, what I should do, really, if I don't do any kind of computing techniques, is that I have to go back to the model. I'm going to use the same model, but I have to estimate the model 6 different times, because each time I have to replace my yi with my y star. That's what equation 5 is doing. I mean, that's, so now you can see that why we make the super strong assumption about A, because if we do that, then we're really only replacing one record at a time. Okay? If you're using any weaker assumption of A, you have to think about all of the other combinations of the different possibilities. So the space that you have to think will be much larger. Make sense? Make sense? Yeah, so the difference between equations 5 and 6, as we circle in the blue circle, is the difference between these two. So we posted here, really, and once, and I hope you have read the section from the paper so you know what we're getting into right now, is that, well, if I have to estimate my equation 5 6 different times, this sounds, and that's only for one record, right? You have to do that for all of the records. And that seems to be a lot of work to do. But recognizing that 5 and 6 are really close to each other, we're able to use what we're going to call importance sampling technique to approximate equation 5 from the draws that we can have from equation 6. That's the short story. Equation 6 is already what we know. Okay, we have parameter draws. I mean, remember what we actually did with this. This part is what is DL even y s, right? This is, I mean, equation 6 in short. And we already have a bunch of draws, if you remember, from the model. So you will see that we use big theta to represent all of the parameter draws from the data. So you will have this if you want. And theta, just so you know, theta are the parameter draws that you have from the model. So this is the posterior of the parameter, right? And then you use those parameters to generate your synthetic data Z. And that's how everything, oh, I forgot my integral here. Okay. So what we're saying here is that, well, we do know how to estimate 6, because that's based on how the model was estimated and how the synthetic data was generated. And we're trying to use them, we're gonna see how to do it, use them as proposals to approximate equation 5 instead of re-estimate equation 5 every time. So I think it's a lot of information, so don't worry, bear with me. And we keep the thought going and then see what we can actually do. But the key here is that there's only a small difference between equation 5 and 6, right? But then we know that to estimate equation 5, we have to re-estimate the model every time we replace a guess with the truth of yis. So we're trying to use what's available from equation 6, which is the parameter draws that we have, in order to get a quick approximation to equation 5. Okay, so keep that in mind. And so what I was writing earlier was this. This will be the multi-color approximation if you want to do it, in a sense that because we already have the parameter draws that we have from the model that we estimate, we are able to incorporate those draws in our final estimation. That's the left-hand side that we're working with earlier. And then you can insert those draws. Well, mathematically, that's what it is. But I mean, in practice, this is essentially multi-color approximation. So you have the draws that you have from the model. You draw them, and then you put them into the estimation. And then mathematically, you do integration, you get the left-hand side. But in practice, is multi-column, meaning that we're doing it for a large number of times and getting it. Okay. All right. So here we are talking about if we have to re-estimate the model every time with changing the y's with y star. That sounds too much. So we're going to use a technique called importance sampling. And we're going to use available draws from this. So this is the model, okay? This is the original model that we used to synthesize the ZL. We're going to use them as the proposal for the importance sampling algorithm. Okay. Now you might be wondering, what is importance sampling? So mathematically, that's what it is. Suppose we seek to estimate the expectation of some function of g theta. And let's just say theta has the density of f. F is really hard to get, okay? However, we could have a convenient distribution, f star, that is slightly different from f, but we can use it to approximate the expectation of g theta, okay? So below equation 7 is what we mean by doing the approximation. The math looks a little bit complicated, don't worry about that. But for us, the most important thing I want you to think about, based on what we were talking about so far, is what do you think are our convenient distribution, and what do you think is our target, or I should say, the density distribution of f theta here. Okay. So just to refresh your memory a little bit, we have a function of g theta that we want to estimate. Okay, we don't know what it is yet, but as you can see, we're using the draws theta from a model that we have estimated to estimate this g theta. Okay, and theta has density f theta, unknown, difficult to get. Okay, but we could have a convenient distribution that is slightly different from f theta. So once we have all of this pieced together, we're able to use equation 7 to approximate the expectation of G theta. So that's why we mean we're taking the expectation with respect to the density of theta here. So that's why it's a small f. Okay? So let me pause here. And based on your understanding so far, don't feel bad if you don't get it. But if you have read the section, maybe you will have some idea. And think about, well, based on what we're trying to do, what do you think are our f star theta? And what do you think is our f theta here? And what can you do from there? Okay, you can use a particular example, either the CE data sample, maybe just the CE data sample, that might be the common knowledge here to describe your understanding. And I'm gonna pause here. We're gonna, come back after the breakout room to answer any questions or clarify certain things, but it's probably a good time to talk to the people in your group. All right, any comments or maybe further questions, clarifications that you want me to make? Anyone? Or is all very clear now? Henrik?
So I was thinking, so if the theta, we said that's the parameters of the model, right?
Mm-hmm.
And so like for the CE sample, it would be like the log income, log expenditure, and like the sigma, like the beta 0, beta 1, and sigma.
Yeah, that's right. Mm-hmm.
The f theta, that would be just the density of those parameters. But I wasn't too sure about what the f star theta would be. I wasn't sure like the distribution, what that meant.
Mm-hmm. Right. So let's maybe take from what Henrik said. So theta in the CE example will be the collection of beta 0, beta 1, and sigma. That is because we use a simple linear regression synthesis model for the CE log income, right? So beta 0 and beta 1 and sigma, they're all on the logs. They're the coefficients, the regression coefficients, and then the standard deviation coefficient for that. I think it's log income regressed on log expenditure. Okay, so those will be our thetas. Good. And then the question now is, my main question is, what is f star theta and what is f theta here? Okay? So f star theta, we know that is a convenient distribution, okay? And what we mean by convenient distribution is, you can think of that as it's something that we know or like we can use. And that most likely, based on the setup that we have, will just be p theta given y, okay? Because that will be a known distribution, okay? This is in the general sense, okay? And the f theta is the one that we're trying to estimate, right? I should say the one that we know that g theta are gonna follow, which is the density that it has, but it's unknown. So we're trying to use what we call important sampling strategy here to get a good approximation, okay? So let me actually come back to the previous slide because I think that probably helps here, okay? All right, so later, so I did prepare like one last section using the CE data to do an illustrated example. But later you're gonna see that all of these pieces, well, this one, if you look at this one actually will be the f theta that we're trying to estimate, but it's really hard to get, okay? But what we do know is that f star theta, which is theta given y, which is how we actually estimate the model, and that is the proposal that we're gonna use later, okay? So if you look at this equation on the top, this part will be our f, right? And this whole part, later you're gonna see be on the g, okay? What we mean by that is you can see that the important sampling on the next slide, I'm gonna come back to that in a minute. We're trying to estimate the expectation of g theta with respect to f, right? So that's why it's g theta times f theta and then integrate out theta. So that's that is a expectation of theta over there. Okay, so it all might seem a little confusing, but like I said, now we're going to move to the discussion of the illustrated example with the CE data, with the model and everything to work with the details. So I hope it's going to become a little bit clearer soon. But this is the general setup of how you can use the importance sampling method to do it for a generic case. But now we're going to turn into the example of the CE data, and we're going to come back to what Henrik was saying earlier, that theta, the big theta here, the capital theta here, will be about the beta 0, beta 1, and sigma. Okay, and then we have our F star, which is the convenient example of convenient distribution, which is theta given y. Okay, and we're going to have our F to be theta given y, but replaced with the guess. Okay, and that's the one that we don't know. It's hard to estimate, but it's very close to the F star theta. So we're using that over there. And then the last piece, which is the piece here that I was circling earlier, this will become our G. That's the G theta that we're trying to estimate. Because at the end of the day, we want the left-hand side, right? So it's easy to, I guess it's very easy to get confused about all of the different pieces going on. But again, importance sampling is actually a really commonly used technique. Okay, so I want you to get the thinking going, and then the next section now we turn to will give you a working example of how things can be done in practice. Okay.